Oh, hello, welcome back. What a surprise. Okay, so what we're going to do now is we're going to be looking at finding time of flight. And so let's say we have a simple projectile. And this one here is going to be a horizontal projectile. And so let's say we have a ball coming on the table. And that ball's coming off and then it falls down to the ground. So it will follow this sort of path here. So how can we find the time of flight? Well, what do we know? We know the height. We don't know anything about its launch velocity, but that's all we know. We just want to find how long is it in the air for. All right, so remember that the x and y components are independent. So if we have the y component going this way and the x component going that way, they're independent. The x component does not change of the projectile, so it's going to be uniform throughout the motion of its flight. The y component is only acting due to gravity, so gravity is pulling that object down. So pretty much it's like the same as if you were to hold a ball and just drop it, it will hit the ground the same time and compared with this ball. In fact, we did that in the last video where we got two different color balls. One fell down, the other one went in a horizontal direction, but they both hit the ground at the same time. So that means that the time of flight, that is t, is the same and y. So t is the same for x and y. So let's see if we can work that out. So what equations should we use? Well, what are our equations? So let's write them down. Okay, so there are our Suvat equations, and we've slightly modified them for y directions, but we can also do them for x directions, and I'll show you that in another video. But let's just have a look here. Here's our change in y. Yeah, we've got the change in y, which is initially, it was 1 point, well, to make the diagram a little bit more accurate, how about we say that it goes up to here. Right, not the bottom of the table, because you have to take that into consideration. So the change in y is 1.3. So change in y, its initial velocity, well, if we're talking about in the y direction, remember, it starts from 0, so that will go to 0. We know g, and we've got the only unknown t, so we can use this one here. Okay. So let's use that. Okay, so we've got this equation here. We know that the initial velocity is 0, so that's 0 there. Our change in y is minus 1.3. So why is it minus 1.3 you ask? Well, because we're starting here, which is 0, and we're going below the original starting point. So its displacement is minus 1.3 meters in that direction, because it's a negative, we've assigned it a negative value. This is 0. G is minus 9.8. So a half times minus 9.8 is 4.9, so it's minus 4.9. T squared. So what we're going to do here is we'll rearrange this equation so we end up with t squared is equal to 1.3 divided by 4.9, and when we do that we get 0.265. Then we take the square root of that and we get 0.57 seconds. So that is the time for our projectile to take to reach the ground, 0.57 seconds. Now what's interesting is if you look at this, we've got a small number here, we take the square root of the small number and we end up with a bigger number. I mean, you know yourself that if you have 2, so if you have 4, and the square root of 4 is 2 squared, so smaller number, bigger number. But what's going on here? Well, we look at the graph of a square function. Goes like that. So we have 1, that's 1. Then we have 2, goes out to 4. So our function here is telling us that if we have a smaller number here, very small, we can end up with a larger y-intercept, right? A larger y-coordinate, I should say. So it looks a bit strange, but it's true. So we have 0.57 seconds here. Okay, that's how you find the time of flight. So from a simple projectile motion problem in terms of a horizontal projectile, it makes it really easy if we can make this equal 0. Then the only unknown, therefore, is t if we know that there. All right, even with the dribbles. Don't you love the dribbles? Okay, so I hope that made sense. I'll see you in the next video when we continue to expand our brain cells.